Good afternoon. My name is David Park. I worked for a number of years with John Browne and his Grassmann algebra, mostly as a student, but also writing a Mathematica application for users. So I'm going to start out by telling you a little about our heroes, and then about what's in John Browne's Grassmann algebra and what's in the application. And then we'll do one example, which is the derivation of coordinate equations for lines and planes in n-dimensional space. This will illustrate how smoothly Mathematica and Grassmann-Browne algebra merge to form a nice contextual exposition of geometry, linear algebra, calculus, suitable for STEM education at all levels. So let's start with our main characters here. This is Hermann Grassmann and John Browne. Hermann Grassmann lived in Germany in the 19th century. John Browne lived in Melbourne, Australia, into the 21st century. So I want to talk about these two people a little bit. Grassmann was a school teacher in Stettin, Germany, who did remarkable work in mathematics and the theory of languages. It is his work in creating an algebra of geometry that concerns us here. Grassmann wrote two books on the subject, one in 1844 and the second one in 1862. They were titled Ausdehnungslehre, or the theory of extension, meaning extension to higher dimensions in space. The first book received little notice, and the second book, which was more modern, didn't receive much more attention. Before Grassmann's death in 1877, Grassmann made attempts to find a position in academia, but was never given one. He received an honorary PhD a year before his death. Since then, and actually quite shortly after his death, I think, many good mathematicians have taken notice of Grassmann's work. William Clifford knew it and wrote a variant now called Clifford algebra. Alfred North Whitehead studied it and wrote a treatise on universal algebra that was an exposition of Grassmann's work in English. L.A. Cartan knew Grassmann's work and used Grassmann's exterior product to develop differential forms and exterior derivatives and applied them to differential geometry. Willard Gibbs knew and admired Grassmann's algebra, but helped devise a different vector analysis that became the mainstay of technical education for over a century. So Grassmann's work was not neglected, but the question is, why hasn't Grassmann's algebra become dominant in the mathematics of what we would call the STEM disciplines? I think the reason may be that Grassmann algebra is computationally intensive and perhaps more difficult than it looks at first sight. Mathematica, along with John Browne's further development of Grassmann's work, can provide the infrastructure to overcome this problem. John Browne studied engineering at Melbourne University in Australia and received several patents for the smooth flow of paper through Xerox machines. He was doing an engineering PhD when he discovered Grassmann algebra and fell in love with it. He switched to the mathematics department and his thesis to Grassmann algebra. It was voted the best thesis of the year. John spent the rest of his life deepening, extending, and clarifying Grassmann algebra. When I first met him through math group and asked him about his interest in Grassmann algebra, he said it was his passion. John wrote 3 books. The first one is Grassmann Algebra, Volume 1, and Foundations, Exploring Extended Vector Algebra with Mathematica. The second one was kind of an interlude and was titled Multiplanes and Multispheres, Notes on a Grassmann Algebra Approach with Mathematica. And the third one was Grassmann Algebra, Volume 2, Extensions, Hypercomplex and Associative Algebras. And I have to say that was a work of heroic endurance. John died in June 2021. Well, now I'm going to talk a bit about the contents of John's books and the application. The application built on John's work is called GrassmannCalculus. Its present size is 84 megabytes with 925 files and 899 exported names. The application is very powerful as it is. Still, I am not satisfied with it because it needs work in creating a smoother interface, filling out documentation, applying it to various fields, writing tutorials, designing courses for various educational levels, and other such matters. This is far more than I can do. This would be significant work of added value. So now we'll look at what's in his books. What's in his book is in the application, but there's additional things in the application. From John's volume 1, we have the basic products of Grassmann algebra. All the foundational products are described by axiom systems. Exterior product implements the idea of linear dependence and independence. It is the workhorse of Grassmann algebra. Ultimately, all products can be reduced to exterior products or scalars, I guess. The number of factors in an exterior product is called its grade. Permutations of its factors introduce sign changes according to the symmetric group. A transposition of 2 arguments changes the sign, but if they are duplicates, it doesn't change the product. So we have the following relation here. The wedge here is the infix operator for the exterior product, and P, Q, and R are vectors. And here we have P, Q, R, P. And now if we exchange the 2 P's, then by the theory, by the symmetric group, we have to change the sign. A transposition will change the sign. But we still have P, Q, R, P. We have the same thing in both slots there. So a thing has to be equal to is negative, which means it has to be 0. And we have a test for linear dependence. The exterior product can be used to build up structures in space. Since basis vectors can be interpreted as directions, they can be used as directional derivatives, and they push us in the direction of calculus. And in fact, that in manifold theory, they almost always use directional derivatives as a derivative operator. The regressive product was combined with the exterior product by Grassmann and was interpreted according to its value. John pulled them apart and treated the regressive and exterior products as separate products, but with dual sets of axioms. The regressive product can be used to find the intersection of several structures, better stated as the common factors of 2 exterior products. products which don't use a metric allow us to do calculations in affine geometry and projective geometry. Oops. The Grassmann complement allows us to introduce the concept of measure and then a metric. It is defined by 5 additional axioms. A point comes in the development when we must supply values for n-squared symmetrical scalars if we wish to continue. This defines the metric for the basis vectors and also allows us to calculate metrics for the various grade spaces. This also introduces reciprocal vectors of which differential forms are one choice. The final foundational product is the exterior product with subsidiary scalar products, that is, the 2, 1 vectors, the normal scalar product that gives you a scalar answer, and inner products of 2 equal grade M vectors, which also gives you a scalar answer. The general interior product will generally give you an exterior product back, and so if it has unequal grades and on each side of it, and it is not commutative and always produces covariant results. So those are the basic products along with the complement. The second book, Multiplanes and Multispheres, was an interlude, so to speak. It will denote multiplanes and multispheres in various forms with Grassmann notation, which is quite handy because you can do a lot of things with notation. But it has a number of routines that Mathematica also has, but with a nicer notation. So it will do least squares fits of multiplanes and multispheres to a set of points with the best fit in each dimension up to the maximum given in a single expression. It will calculate orthogonal points and intersections. It will calculate inverse multispheres. I guess I left out there. It will also do intersections. I said that. It will calculate inverse multispheres. It will calculate tangent multiplanes to points on multispheres. And then he has a chapter on Clifford's circle theorems, which I haven't looked in all that much, but it's quite extensive, and I guess introduced us to new methods that Clifford discovered. And you can take the circles and find their intersections, and then get lines, and then get new circles and get new lines, and it kind of goes on. And then he has a chapter on simplexes, which is very useful. The book he wrote was on hypercomplex and associative algebras. This book introduces the Grassmann generalized product, the gateway to the hypercomplex and associative algebras. The generalized product has a variable parameter or order, usually called lambda, which is summed from 0 to the minimum grade of its 2 arguments. Each term has, and you can think of this started with as a list of terms. Each term has a symbolic sign, and at one end of the list it's an exterior product, and at the other end it's an interior product, and in between is kind of a sum of them. And terms all have signs, and designating these signs determines what properties the algebra will have, what kind of algebra it will be, whether it will be associative or commutative. And John has a list of about a dozen things, which I guess are talked about in advanced algebra books. The hypercomplex algebras give us complex algebra, quaternions, octonions, tessarines, split forms of the algebras. The main associative algebras are Clifford algebras, of which there are several forms. John also implements the Pauli and Dirac algebras with their matrices as basis vectors. John asked me to put in derivatives, so I added the following to the application: directional derivatives, differential forms, and spaces that have explicitly defined coordinates. There are also form integrals that integrate differential forms and take their domains from the Mathematica geometry routines. And this is a very nice example of how Grassmann algebra can mesh with Mathematica, and it's just beautiful. So now I want to go into an example. And what we're going to do in this section, we will do a step-by-step development of calculating coordinate equations of a Grassmann line in two spaces, a little bit too simple. Yes, two spaces, a bit too simple. This gives us an outline for writing a general routine. We will then see how to go back from the coordinate equations to a Grassmann representation of the line. We set a coordinate bound vector space that has explicit coordinates in an origin, and that's done right here. And a bound vector space is going to mean a space that has points. And this is three-dimensional, and the coordinates are x, y, and z. I have to evaluate that. And I echo back the Grassmann coordinates and the bases. And you see the bases, even though we're in a three-dimensional space, we have four basis vectors. And the first ones are kind of expected: e sub x, e sub y, e sub z. But the first one is what's called an origin. It's a reference point. It's like a stake in the ground. And that allows us to have explicit points that are part of the algebra. And we don't just say like, well, this list of three things is a point, and this list of three things is a direction. It's in the algebra, and you can identify them. Here is a line in Grassmann notation. A line is given by a Grassmann form, which is a point, wedge, exterior product of a point and a direction. The direction, which has no position in the plane and probably should never be plotted, is now bound together with a point that does have a definite position. Together, they define a line that passes through the definite points. And this is my method of replacing numbered equations, which I don't think it should have any place in Wolfram documents, but that's another subject. So here's here is the point that anchors the line, and then this is the direction. And this point is just, you can just think of it as it's a point and its coordinates. That's it. Very, very contextual, very explicit. We also expand the exterior product, representing the line to a canonical form. If we later represent the line using a different point on the line, or using 2 points instead of a point and a direction, the Grassmann expression will look different, but the canonical expression will be the same or congruent. So this is the congruent form. This is the canonical form, and it's made of a weighted sum of bivector products. Okay, so following is a general position point using coordinates x, y, and z. It can represent any point in the space and will act as a kind of probe. Some values of x, y, and z will give points on the line, and others won't. So this is our general position or probe. if we wedge the general position with line 1, then the general position will be a point in the line only when the entire expression is 0. The expression will act as a filter that lets through points only when the entire expression is 0. So that's it. And now, so this was the line. The two factors that made the line. And this is our probe general position point with X, Y, and Z in it. We then expand the filter into an expanded sum of the grade basis 3 vectors. And now we get a sum of 4 terms of trivectors because we've added the probe in. And the coefficients are linear expressions, like minus 13 plus 3x plus y. Because this expression is linearly independent, it will only be 0 if each of the coefficients of the basis products are 0. So we extract them using the Mathematica coefficient routine. And we get 4 linear expressions, which are the coefficients. We have 4 expressions that must all be 0. Are they all independent? It is often the case that they are not all independent. We can use the Mathematica routine Grosvenor bases to select an independent set of linear expressions. And this is actually a rather trivial problem for Grosvenor bases, but it's a nice introduction. And so when we do that, we get just 2 linear expressions. And if those 2 linear expressions are each 0, then all the 4 of the ones before will be 0. So there's only 2 equations. We thread them over 0 and then turn them into nice equations by putting the variables on the left-hand side and constants on the right-hand side. So this is our final answer. These are our equations. 4y plus 3z equals 13, and 4x minus z equals 13 also. And I wrote a routine called generate coordinate equations, which will solve these kinds of problems. So now let me go close this and look at the other side here. We can map both ways from a Grassmann expression to equations, or from equations to a Grassmann expression. Let's regenerate our data for the equations in the previous section. I do this using generate coordinate equations. This has an option which says do you want to have association output? And I say true. So this will give you output that it will give you association with keys and entries, and then there will be everything from the input that you started with, the first Grassmann equation you used, and all the intermediate steps, and then the final output. So I evaluate this, and I get up a palette. I should have made it. Okay, there it is. And so now if we want to do something, this is a general palette that will work for any association that's just a single level. And so this was case 1 is a name I gave to the output. So I can just click in. Oh, did I mess this up? Oh, yes, I did. If I can type case 1, and then these are all my keys in the association, and the multiplane is the input. And then I could say, make an arrow, let's say, and then type case 1 again and pick the output. And so then that gives us our equation, the input line and the output equations. And you can compute with these things, so it's kind of nice. We can generate a Grassmann representation for a line by generating points from the equations using a Mathematica find instance. The following generates 2 points from the equations, converts them to a Grassmann expression, and checks if the result is congruent to the initial line expression. So this is another device I have, an evaluation button, which would actually evaluate all that if it wasn't there to begin with. What all the code for this, all the statements that generate this are in a little thin semi-permanently closed cell, and you can get at it, but I'm not going to try here because it doesn't always work with this style sheet or something. So anyway, we use find instance to find 2 solutions to the equations. We feed them the equations we generated, and then we change them. We feed those into the position vector called the probe. Now it's kind of a template, and so that gives us 2 Grassmann points. I have the O in there. And then we change this to a line 2 by using 2 points. Before we used a point in the direction, but now everybody knows the line is also given by 2 points. And this is kind of a refactoring. And line 1, I just show it for comparison. So now I take these 2 lines, line 2 and line 1, and expand into a canonical expression, and they have the same part here. This is all the same, except that line 2 has a constant in front of it, and so they're congruent. There's a routine to test if they're congruent, and they're congruent. So that's it. I hope I didn't run over the time. We do have a Grassmann Algebra circle. We're meeting on October 21st. And if you would like to attend, you could send me an email from the my email address up here. And it's just a kind of we just have general discussions and explore things and try to learn. So that is the end.